get into the presentation mode. Good morning all. It is so a good day everyone, ladies and gentlemen. In this first session, we are going to look at just the basics of the DMS process. We're going to look at the overall picture, start at a low level and work ourselves up during this presentations, and we'll conclude then with a bit more detail in terms of how the cyclone and the process interact with each other. So I'll start off just with introduction. We look at the basic principles. We'll look at why we use dense media separation, and then we are going to look at the dense media process flow sheet. So why do we use, or what is dense media separation? It is a gravity separation method whereby you use magnetite or ferrosilicon as a media to induce a separation density. You don't use water, obviously, because water has a density of 1. We need something else to create this artificial density. In order then to float a material to produce a separation, and the denser material settles then or go to the sinks fraction. This picture just shows how you can float a rock. If the picture on the left-hand side, you have water and you've introduced solids, and obviously everything sinks to the bottom. But if you introduce then this artificial media, consisting then of magnetite and water or ferrosilicon and water, you can control the density up to the point where you can float rocks. And that is the principle of dense media separation. We want to float a certain or separate at a certain density. Now, in the mineral processing environment, you have physical processing, where you change the characteristics of the material, but more the size, where you break particles down or you bind them again together to form things like pelletizing or briquetting activities. But then you also have the extractive processing at the bottom end. And that is where you are now producing or upgrading a ore body to extract the mineral that is associated with that ore body. And that is where dense media separation fits into the equation. So why dense media separation? First of all, you want to separate the valuable from a waste. That's one of the options you have. You can do pre-concentration of minerals before a process like comminution. And that's an example in nickel and platinum, where you separate a portion away from the milling process, and only the valuable material gets further processed, so you don't waste energy. Pre-concentration, where you want to reduce the footprint of a recovery section, like for diamonds, for example, because this recovery section operates at low tonnages because it needs to make very important decisions. It needs to recover the diamonds. So you reduce a big portion of the material coming in so that you don't overload that process. And then also to upgrade the valuable material to meet a specific quality, like in coal or in iron ore. And by changing then the density, you alter the quality depending on market requirements. You'll see this picture or diagram during the course of all these sessions. But the dense media process consists of a couple of factors. Ore characteristics, cyclone design in this case, plant operation and medium characteristics. But in this discussion now, the ore characteristics. One needs to know what is the ore characteristics. Is it amenable to dense media separation? So you've got an ore body, this picture illustrating a coal seam that you'll find underground. And now you need to decide what methods is available to do the separation. So there's a couple of properties that you're looking at. that is to your disposal. You can look at appearance, density, magnetic susceptibility, electric conductivity, or surface properties. And wherever there is the density difference between a valuable and non-valuable, then dense media separation is a very viable option to consider. You may sometimes have multiple options to consider in order to extract this valuable from the ground. And whichever one is then more economical, that's the one that you would normally then choose. So you've got material that's consisting of different densities. In this example, it's a laboratory environment, so it's a liquid form that's been used, organic liquid. If you introduce this material into this liquid, in this liquid has got a density in between these particles, then you can separate the particles. The light or the light density material will float to the top, and then the heavy material sinks to the bottom. Now, in this example, there's no time constraints. You've got a near perfect separation. If you plot this on a density scale, so on the x-axis, you've got different densities, and you will see the density here is relative low, so it's applicable to gold. Then if you want to separate the light fraction shaded in blue from the heavy fraction shaded in gray, if you've got perfect separation, then you will have a clean cut at a specific density. Whatever that liquid density is, there you will have your separation, where the portion that sits to the left will then float, and the portion to the right will go to the sinks fraction. You will see this graph here, it's fractional values, and you will have your light fraction sometimes intersecting or overlapping with the dense fraction. And that's where you have to make a decision, where is the optimal point to set your density in order to initiate separation. When you introduce material into a dense medium vessel, then you'll find or realize that there's time constraints. There's also other factors that affect the separation process. So the objective is to look at the dense media process and dense media cyclone or separation vessel, optimize it to the best of our ability so that we can get as close as possible to a perfect separation. The graph that is seen on the top right, you'll see that the dotted line was the perfect separation. But now this curve has obtained a slope. The slope pivots around the 50% point. That is the cut density that we refer to in dense media separation, and that is the particle density that's got a 50% chance of either reporting to floats or going to the sink fraction. Now, because there is now a time constraint, we do not get perfect separation. So the two shaded areas represents a portion of material that's now getting or has got the probability of being misplaced. So on this curve here, this area where the mouse pointer is, that is light material that is now getting misplaced to the sinks fraction. And the same goes for the heavy fraction or the fraction denser than the cut density. If your circuit is not operating correctly, then this shaded areas starts to expand. And more material is now getting into this probability range of being misplaced. And that is what we want to prevent. We know we aim for perfect separation, but we know we can't really get that. So we just need to minimize. And that is what these sessions of today is all about. What are the factors that we can exploit or look at to reduce then the amount of misplaced material? Just a couple of flow sheets, typical flow sheets that you get in the dense media process. In this application, you've got coal. It's a bit busy, but you've got your incoming material in the top left hand. It will go through the different processes, and you've got your different products at the bottom end of the page. Your dense media cyclone sits in the, or dense media separation process sits in this position. You can have multiple stages, and you can also have different size fractions being treated by different vessels, in this case, dense media cyclones. The left-hand section is more water-based. I will not talk about that today. In iron ore, same principle, material enters at the top left, and you've got your different products leaving at the bottom end of the page, and dense media separation, again, in these different positions. In diamonds, that's where you typically find the dense media vessels. And then from there onwards to the recovery section that I mentioned earlier. That is the unit that do not want a high tonnage. It needs to have low tonnages to do a proper separation. And then in platinum, you've got a dense media process in some applications, and take note, the sinks fraction is now reporting to the primary mill section. So this is the application where there's pre-concentration. It depends on the ore quality, if you can exploit this option. But if possible, that's quite, it is an option that could save you energy and reduce the load on your mill circuit, and also induce possible energy savings. Bring it back to a more simplistic process. You've got your incoming circuit, your feed preparation position. You've got your separation section, and then you've got your media reticulation system. We'll discuss each of these pieces of equipment in a brief description in the following presentations. But just for those who's not completely familiar with the dense media process, you have your raw material coming in, raw coal feed in this example, and you introduce the media with the coal. It goes into the separating vessel, being a bath or cyclone, and you have your separation between clean coal and rejects. The media also gets split into different directions, a portion following the clean coal and a portion following the rejects. You've got drain and rinse screens. The purpose of these screens recover the media. A portion of this media is correct media, but then you need to introduce wash water, and that becomes dilute media, and you then recover that, and that's how the media circuit fits into this process. Back then to our basic flow sheet. Let's look at the feed preparation screen. So what's the purpose of the feed preparation screen? It needs to prepare material before entering the dense media circuit. You can't just send everything from the run of mine after it's been crashed into a dense media vessel or dense media cyclone. It needs to be screened into the correct size fraction. If there's any inefficiencies on those feed in that feed preparation screen, then you're sending the wrong size fractions, or you in the wrong direction. And you'll see later that this can then lead to some yield losses. Yield is the word that describes the recovery of valuable to your product stream. Adequate water addition is required on a feed preparation screen, as well as then proper screen maintenance. People sometimes neglect that. Pegging and blinding of the screen panels can be a problem. Your panel aperture must be larger than your drain and rinse screen. It sounds maybe quite basic, common sense, but you'll be surprised. Sometimes this does not happen, and maybe later we'll discuss an example where this occurred. And then if the feed material characteristics change, your size distribution change, for example, one just need to relook at your design of your feed preparation screen to make sure that the unit is still adequately sized, capable of handling then the change in feed conditions. This picture on the left-hand side gives you an indication of what blinding looks like of apertures. And on the right-hand side, that's what pegging is looking like. Do not underestimate what this can do to your process. If you've got a scalping screen where the top fraction needs to be recrashed, the fraction that is suitable to go through to the dense media process goes to a bottom deck, and you screen out your fines. If you've got a process like that, this can create a problem for you because you can't get material through to your dense media process. It keeps on running back into your crushing circuit and create all sorts of production problems. Picture of an overloaded screen. You can see there's a high fines content present in this material going into the mixing box. That is not what we are looking for to provide optimum feed conditions to your dense media process. So that's just the purpose and some pointers on the feed preparation screen. Then your circulating media sump. The function of this sump is to collect the circulating media that's used as a storage or buffer entity that is keeping the media available in order to be pumped to the mixing box where the ore and the media is then mixed. Can be then the media, as I mentioned earlier, can be ferrosilicon or magnetite. The relative density in this sump can either be at the correct cut density or operating density we want to be, or it can be of a higher density. And then you add water in the suction of the pump, and that controls then the density to your mixing box. The correct medium sump receives then the feed from the densifier underflow. We'll talk about the densifier just now. The drain section from your drain and rinse screen, and then the magnetic separator over dense, which we'll also discuss in this presentation. Normally, the density in the sump is larger than the operating density. That allows you for the introduction of water, which is more the common method, the more acceptable method of controlling density, because that allows you to make density changes quite quickly if need be. The operating density, in other words, the density in this pipeline going to your mixing box, is generally lower than the cut density, depending on the type of vessel that we're using in this process. The separation vessel. Now, the separation vessel, if you need to design a separation or select a separation vessel, one of the things you have to look at is the size fraction that you want to treat. So there are different types of separation vessels, and the dense media cyclone, which we're going to focus on more in detail during this presentations, is one of them. But sometimes there are other vessels that is more suitable to be used. And then also at what operating or cut densities do you want to use these vessels? Not everyone can be always used for all the densities. So your bath type washers, typically a Wemco drum, a Drew Boy, a Tesco bath, Daniel's bath, they treat normally large particles, because large particles, if you want to put it through a cyclone, you need to have a large inlet opening, and that's not always economically, because a large inlet opening requires large volumes. The medium grade, normally coarser, as you don't have any centrifugal forces going through this vessel. Your medium differentials, in other words, you'll hear the word later again, described in a different presentation, but that's the difference in density between the overflow or your float stream and sink stream, the media that's leaving those two positions. They've either got a similar density, then the differentials is low, or they've got a high difference in density, and then the differentials is high. The footprint is normally quite large for these pieces of equipment. That is just some examples: Daniel's bath, a Drew Boy, Tesco bath, or Wemco drum, but there are other vessels as well that's sometimes used in these applications. Then the centrifugal type washers, that's where the dense media cyclone fits in, but you also have products like the 3-product cyclone that's coming from China, a Dyno Whirlpool, Lacodem, and they normally treat the finer diameter particles. Although on newer designs of dense media cyclones, you can treat particles up to 80 millimeters through a dense media cyclone. Generally, the finer fractions go through dense media cyclone because of the assistance of centrifugal forces. You can't rely only on gravity. It takes too long for the particles to be separated. The medium grade that you use, normally finer because of the centrifugal forces. And then you do have media differentials. In other words, there is a difference between the overflow or the floats and the sinks densities. But the footprint is normally small to medium, and that makes the dense media, the centrifugal type washes, quite attractive in most dense media applications. Picture on the left-hand side of a 3-product cyclone. You've got your dense media cyclone on the right-hand side, Dyno Whirlpool, and then your Lacodem. Each of these pieces of equipment has got its advantages in certain applications. Then your drain and rinse screen. As mentioned now before, your material that's been separated needs to be, there's media associated with it, and we need to recover that media. So the purpose of the drain and rinse screen is then you've got a drain section where you drain the excess media. And then you've got the rinse section where you add wash water, and that washes off then the media from the gravel, and we recover the media. You don't want to lose media. However, your media consumptions typically for ferrosilicon is about 150 to 300 grams per ton, magnetite 500 to 1.5 kilograms per ton. Obviously, you want this as small as possible. Screen panel aperture smaller than the desliming screen. And when you've got problems with your drain section, you can use static bends or sieve bends, static panels or sieve bends, in order to increase the drainage, so you don't overload then your magnetic separator. If you have poor drainage on the first section, it carries over to your drain section, and then it overloads the processes following the drain and rinse screen. And then if you have poor washing on your drain and rinse screen, then that leads to media losses. Example of a worn panel, that's what it looks like. So proper inspections required. And then on a drain and rinse screen, the sprays needs to be covering the whole width of the screen. This is just an illustration of a poor drain and rinse screen. So you do not wash off all the media from the particles. Then the densifier and dilute circuit. So you dilute media, that receives now the rinse, the underflow from the rinse section, because you've now introduced water. You've got your densifier overflow, and then spillage from your sump pumps. The sump then acts as a buffer or storage for your magnetic separator. The densifier, the purpose of the densifier, which is this unit situated here, is to remove excess water from the correct medium. The densifier overflow, because it contains some media, it goes to the dilute circuit because you need to recover that media. You can't let that stream leave the circuit. And it provides then overdense. The underflow of the cyclone is a high density, and that provides then overdense for your correct media sump, which then thereafter you can add water to control your density. These units are normally quite small in diameter, so oversized particles can block that the outlet of the densifier, and do not underestimate what that can do to your process. We need to if you've got densifiers, you need to make sure it's operating correctly. And then the use of the densifier depends on the operating density that you envisage. You don't have to use densifiers all the time. There are many dense media separation processes that don't have densifiers, but there are that do require densifiers. On the magnetic separator section, in this picture, you see on the left-hand side, you see a primary and a secondary magnetic separator. These days, there's only one primary magnetic separator. There's going to be a session in more detail on magnetic separators later, but this just shows you then what the magnetic separator looks like. And what's the purpose? It receives then the dilute media, and you need to recover the media, the magnetic media. It's also cleaning the media for non-magnetic material. A poor performance of the magnetic separator can affect the performance of the dense media cyclone. And then sometimes demagnetizing coils are normally installed on the overdense. The overdense, you've got the rotation of this drum. The material comes in on the right-hand side. There's a magnet. It recovers then the magnetic material, and the non-magnetic material leaves then in a different direction. But this magnetic material that's been recovered has got residual magnetism. And then you need a demagnetizing coil just to break that attraction forces that's still present. There are different designs in terms of magnetic separators, concurrent, co-current, and self-leveling. And then there are occasionally design improvements in terms of the strength of the magnet on the magnetic separator. Some of the things that you, or factors to keep in mind, and as I said, there's going to be a more detailed presentation later, your operating level, magnet position, gap between the drum and the discharge lip, and then the height of the drum. These are all parameters that play an important role, because this picture, when you look at this magnetic separator, if you walk past, you may not notice anything strange. But if you look carefully, you'll find that there's more turbulence on one side than on the other side. And that's an indication that there's something wrong with the throughput or the flow through this magnetic separator. So it's paying attention to detail. Because if the magnetic separator doesn't operate correctly, it's got ramifications during the rest of the process. Obviously, you want to reduce your media losses. So you have adhering losses for your drain and rinse stream. That's one area to look at. Magnetic losses for your ineffector when your magnetic separator is not working effectively. You have contamination losses when there's too much non-magnetic material. And then you've got your housekeeping losses, where people just leakage of pipes or poor operating procedures. Corrosion losses can sometimes play a role, especially on ferrosilicon, and then losses due to inferior media. People tend to sometimes look only at the price of the media. They choose a cheaper media, and then the media is inferior, and the performance gets affected of the equipment. And then clients want to know from the suppliers what's wrong. But meantime, it's the client that is trying to save cost. This graph illustrates, it's got a lot of data points. That is sampling results from a coal plant that's using proper mechanical sampler. Now, this variation is due to all fluctuations coming into the process. The point to illustrate, and there's going to be a presentation on sampling as well, is that without proper sampling, you would have had a wider spread of data points. And you have to control your plant based on data that you receive from your ore leaving the system. If you've got a wide spread of data, how do you control? This is the last couple of slides. I know it's a lot of information, so let me quickly try and just guide you through this. It's a coal washing plant, total throughput 2,000 tons per hour. You've got a coarse section, small section where the cyclone would fit in, and then a fines section. The ultra fines is normally flotation. There's no, that hasn't been incorporated. So though that's a typical wash cost, but that's a couple of years ago that this was, this information was obtained. You've got then the different quality, the efficiency of separation on the second line. There's the qualities, the yield that you get, the product tons per hour that's coming from the process. And then we look at the production cost based on the information that I've used in this section here. And I've used a coal price of $80 per ton. To sum it all up is if you subtract the value generated and the cost that's incurred, you end up per annum, in this example now, of around 550 million rand per annum, South African rand. Now, if, and I'll go back to the previous slide to show you the change. If you change the efficiency on the cyclone by only on the third decimal by 1 point, and let me just go back to show you, it was an efficiency of 0.15, and we slightly increase it to 0.16. Then per annum, there's a 23 million rand possible loss. And that is the point of making sure that you control your plant correctly. Having proper sampling equipment, making sure the plant operates correctly, making sure that the equipment that you use is operating correctly, because that small difference is costing you money. And then in terms of the effect of magnetite, in this case it was coal again, but you've got ferrosilicon as well in other processes. If you look at the bottom end here, there's the magnetic consumption that I've used in this calculation, 0.5 kilograms per ton for the coarse fraction and 1 kilogram per ton for the smooth fraction. If I increase it to 1.5 and 2, which is not uncommon, then that leads roughly to about 8 million rand loss per annum. Do not underestimate the effect that your medium can have on your process. So in conclusion, the dense media process consists of various pieces of equipment, but it's linked together to form a system. And that is what we are planning today with this presentations. We talk about the equipment, and then we're going to all bring it back into the system. Thank you very much.